ಆಡಿಯೋ ಬತ್ತಿಲ್ಲ.
Okay, so hello everyone. Welcome to this live session. So we'll be talking about medical image analysis. And I'm Jagriti Patel. I'm a fourth year PhD student at IIT Gandhinagar. I work with Professor Karla in the Medical Ultrasound Engineering Lab. And my research is on quantitative ultrasound for soft tissue characterization. For now, I've been working with human brain samples and then trying to discriminate if we can try and differentiate types of tumors. There I'm trying to work with glioblastoma, and then here as part of my thesis I'm working on high frequency quantitative ultrasound based techniques to characterize oral cancer lesions. So that's also a different tissue that I'm targeting at. So for this particular course, this is like a 4-week course. The first week plans as that you have different imaging modalities. And I'm a PMRF NPTEL TA, and the role of me is to first give you a short summary of what the lecture was all about, and then followed by Q&A. And now, if you have some questions, you can do. You can ask me. Feel free to unmute yourself within the session, or else by raising an hand also works. I can just say out your name from what is visible to me, and then I'll be sharing the previous year assignments and the solutions to the same, so that you will be able to solve this week's assignment, which is like due on this 25th. For this particular course, since you know that it's on medical image analysis, so we'll be focusing on imaging modalities, and then further followed by how image classification, how do you do different types of image processing. There is a prerequisite that you should know a little bit of image processing, so that you can understand simple things as doing filtering like median filters, smoothing, some low pass high pass filters. Then you know something about averaging, probably white noise and those kind of things, grainy things, so that you'll if you will be comfortable sharing the future slides with you, and you don't need to go again. If you want to, there are plenty of lecture slides which are being shared by professor on the online session. Also there are books followed by it, so if you want to have a look, you can always go and check them. I have personally checked all the books that have been shared in the online session. They are directly available, and the PDF copies for it also you can directly download it. Additionally, all of this course content that I'll be sharing now, this week's recording, the lecture that we are having right now will be recorded and will be later posted onto YouTube, so that you can have a look offline also whenever you need to. So, in case you do miss at time, you can always go there. The link for the same would be shared by NPTEL team. So, for that, you'll need to be active on the portal. In addition to that, on the portal you have a discussion forum. So whenever we are not able to meet at times, then you might address your questions on the discussion forum, tagging a particular TA if you want to, or you can just generally mention a TA there. So with that, let's just start with this session. Like Professor mentioned, so this course is by Professor Devdutt Shil from IIT Kharagpur, and we all know that since this medical image market has been like predominantly increasing and increasing, and furthermore it's everything is for translation for better human health care and all. So we do see, so the stats are not particularly for India, but there is like a heavy market towards and in the future for this particular field. And then there comes something as a phantoms market. So whenever you have an imaging modality, you need to so that imaging modality will work on certain principles and some algorithms. In order to validate those, you need to have some phantoms. Now phantoms here doesn't essentially mean as ghosts, which they are in literal human terms, but these phantoms are something which mimic our own tissue, which has a similar acoustic and viscoelastic as in mechanical properties, so that we can validate our imaging algorithms, modalities, and principles first on them, and later followed by in a small animal models, and thereby after those in ex vivo human tissues, and then later doing it everything in vivo in humans. So that market is also predominantly increasing. So you do have further future in this particular field if you are looking up to, if you want to further engage into. So there are like, I'll just give you a brief overview and we'll stop our overview at CT, because doing one like 4 5 modalities altogether is like too heavy. So we'll do X-ray and CT here. I won't go into in depth. It just um touching upon those areas to an extent how professor did, and then later we'll look at MRI and ultrasound in the next week's lecture along with the segmentation and classification techniques, because they are like, if you teach MRI and ultrasound all together, so both are like two independent big heavy topics and also big heavy modalities to learn from, whereas X-ray and CT are like more or over same. Whereas also like MRI like has a link towards CT in terms of how it looks and how its mechanism work, but entire principle is different there. Okay, so these are like different medical image modalities you have. First one is X-ray, which was like coined up by Roentgen in 1894. Then you have like CT scan, that stands for computed tomography. You have magnetic resonance imaging. Then you have ultrasound, histology, and positron emission tomography. In addition to these techniques, we also do have many others, like you have SPECT and then you have NMR and all. But these are like the main which control the entire medical imaging market. So let's say first you want to see if you do have some abnormality, let's say you're facing some pneumonia kind of diseases, and person will directly tell you to do X-ray. Or let's just say you fall off from somewhere and you got a sprain in your ankle, you'll be able to do X-ray. Whereas now your bones are not broken there, but now we need to see if your tissue is broke or you do have some ligament tear or something. Then they'll ask you to do CT and then further follow it by 2 MR. So and then how one particular thing necessitates the other thing is how this pipeline is being followed again there. And then there's this non-invasive portable technology that has been followed for some years now, that's ultrasound, in which I have been personally working into. So that's a medical imaging modality that I work in. And ultrasound nowadays is like almost available for all particular like all imaging of our human body, and it's also a bit much more inexpensive with respect to the rest that we are looking at. It's also non-ionizing also. Okay, and then the gold standard always remains this histology, where you take some part of the tissue, send it to laboratory so that they'll do this blood sample analysis, tissue characterization based methods. Those are like molecular methods that will just see in the how the tissue is being progressed, how, if there are different cells in it, how the cellular morphology is being changing. Something that imaging modalities will tell you about, but will tell you an effective representation about them. Whereas histology always confirms the presence of these techniques and gives them an upper hand that okay, this can work. So how the drive today in today's generation is that you take this forward, make all of your characterization using this medical imaging to an extent so that you can beat up histology, you can be comparable to histology, so that doctors do not, whenever you have a tumor or something which is abnormally behaving in your body, so doctors do not need to excise an extra part there of your tissue, and the normal margin that they're trying to resect, it would be much more lesser, so that you do not have further side effects in the future. Okay, and that's how, so that was your the conventional and traditional imaging modalities, followed by it. So everything will give you a data towards the end. And nowadays, the field is like going towards data-driven analysis. How data-driven analysis works is like you do some quantification, register them, try and differentiate and classify, detect it, segment it based on, let's say if you have speckle is nothing but made up of multiple grainy texture that you look on an image due to some constructive and destructive interference of the waves that you're getting in. Now, how the speckle changes whenever you're trying to image, or how your grainy texture in the image changes. If it's similar in certain areas, that means that you have localized one part of tissue different in other areas, that's different. You label those pixels there. So that is something as segmentation. And then further, entire thing is nothing but encapsulated within image processing here. Okay. So here's how this 4-week lecture is being splitted into, and that's how Professor told in the on it's like in the recorded lecture. We have medical imaging, through which we have these imaging modalities as CT, MR, microscopy based techniques which are like done for pathology. Then you have OCT. OCT is optical coherence tomography. So that's being done for eye, whereas like you take an image of the eye from the fundus layer, from the retina, choroid, and you do see if there are certain problems in there. So let's just say, so now whenever we go to an opt, first check he'll do is like he'll have us read the entire table and alphabets that we are seeing from apart. But after a point, he does go let us go to an image, to a setup where we have to place our chin there and just image it, look at some points, look at a house or some green land or so. Now, through that, those kind of imaging modality, those are also something diagnostics that we see into. That's one is like fundus, then you have angiography, then you have this as optical coherence tomography, all of which are like high resolution imaging techniques so that you can see our eye. And our eye is not much bigger, it's like 2 to 3 centimeter region that we have to look around. And the layers that we have, choroidal, retinal, are very important for us to process our vision. So, those are like vision processing layers that we have in. And if you do have some layers or fibers or some plaques in your retinal layers, might lead to for the vitreous humor to flow in through, and you might have vision loss towards the end. So these techniques help us to see there. Then you have organ appearance, which can be done by the imaging modalities that we have. Followed now, everything which looks beautiful on the outer side does have some physics playing into. So you have tissue engineering interaction. In case of X-ray, you have the photons interacting. CT, you also have the electrons interacting there. In magnetic resonance imaging, you have the proton spin. So how a hydrogen ion spins around, and which gives you which leads towards a production of a magnetic field, and towards the end it moves with a resonant frequency leading to a Lama frequency and hence a magnetic field. And then you can just compare, interpret, you have different echo appearances there. Then you have ultrasound. Now everything in ultrasound is just a sound wave propagating, but all of these other modalities, it is nothing but you CT and MR, you go into an gantry and image yourself. So in terms of MRI, there would be multiple magnets around you and then multiple magnetic detectors. So that's a big gantry. For CT also, you do have the same thing. For X-ray, it's like X-ray has no attenuation when you are in air. So X-ray doesn't attenuate in air. So if you just stand before the source and your detector is behind, it would give you a pretty nice image. Whereas ultrasound doesn't work in the similar manner. Ultrasound cannot propagate in it needs a medium to propagate, cannot propagate in vacuum. So there, you everything in ultrasound will need water, will need some coupler. So first, a better coupler is nothing but water for most of the imaging systems. If not water, because every time to do ultrasound you won't have water around, or you won't go into a tank of water, an aquarium or something, to so get yourself a sonography image. So what they do is like they do have this electrolytic gels which will help you couple the impedance mismatch in between your skin and the transducer that you are trying to image with. Okay, now here transducer, what I meant will, if you have looked at the slides, it's nothing but a piezoelectric crystal which converts an energy from one form to another. In this case, it's mechanical and electrical. Okay. Then you have this image processing and graphic techniques that we just talked before, that segmentation, denoising, you have visualization of them. And then you have machine learning. Of course, like nowadays, it does not even need an introduction for it. It's like prediction, example, complex reasoning, classifications, those things. So for our traditional image modalities, this is how the workflow goes. So every time there's a trade-off in between There's always a trade-off in between your frequency of imaging and your depth of penetration that you're trying to look at. Okay, as in how your frequency increases, the resolution of imaging also increases. And as we all know that mu is equals to C lambda. So here frequency, sorry, did I wrote it wrong? Is it going?
C
Oh,
by
sorry.
lambda.
Sorry. It's not working. It's not letting me write. Let me connect it again. Ah, yes. What someone else just said now. This is not working. 2 minutes. So if I share screen, I hope it works now. Is my screen visible? Ah, yes. Okay. I don't know what happened. Probably network or something. Yeah. So, I so C is equals to mu lambda. And then we know that, yeah, how someone just said now. So both are like inversely proportional to each other, frequency and the wavelength. So every time whenever your frequency increases, your depth of penetration decreases. How? So if you have a high frequency to image at, it will give you better images, good resolution. So there's nothing as good or bad any times, but yeah, your resolution will be improved when you're looking at superficial structures. However, if your frequency is lesser, then you might prefer to go into abdominal or deeper structures, as perhaps cardiology based structures, abdominal imaging and those. Okay, so here what we look at, you have like penetration depth with respect to resolution given here. And this is like a type confocal. Here is a type of imaging which helps you image at multiple planes all together at one time. So I'll give you an example here. So people work with this micro bubbles. Micro bubbles, so you can consider them as equivalent to air bubbles, but the size is in microns now. And this micro bubbles do have something as a lipid based shell, and inside it has an air. Okay, now whenever just imagine if you're putting a slide and then you have these micro bubbles on top of it, it would flow up, or else at times not flow up, but it was like it won't stay on a single site at a time. And then whenever you're doing like bright field imaging, you'll have multiple planes all together. So depending on your magnification and where you're focusing on, as well as your depth of field of the microscope or the particular aperture that you're looking at a time you'll only be able to image one single plane, and you'll have the shadows in your image which will tell you that in some other plane, in some different field, I'm being able to see a different population there. So confocal is a type of imaging which helps you take multiple angles at a time, multiple planes of interaction. So it goes into layers and layers of your particular field that you have. And towards an end, it will give you one processed particular image, which will have your entire field of population that you have inserted into your slide or like fixed into your slide. So that's like a very high resolution based technique. But again, in terms of confocal, it's only limited to for research purposes, for histopathology, for path lab based searches. Then you have this ultra high resolution OCT based techniques that we just talked upon, that for eye ophthalmologists usually use this kind of technique so that they can see the structures at choroid then at retina, because these are like most important. Then you have conventional OCT based techniques, which are nothing but have been used by researchers to look at the eye lens, has been used to see the length of your eye, this particular to gauge the eye. So in cases people do have cataract surgeries, they need to replace this lens, the choroidal in front of it. So at times they use it to measure the gauge length over here. So for to measure the gauge length for opthel, it's not been that developed how it had to be and how it was for different fields for different organ imaging. So how they have been doing is like they'll fixate the eye on two ends and then like just stretch it apart, and then they'll place a standoff of water in top of it, and then they have their OCT imaging system there. Nowadays you just have to sit and pinch up there, but that instrument do not tell exactly the size of it. So hence we are like just ended up using an approximation of the lens which will give you a correction there. Not going into in depth of it, but yeah, that's how conventional versus ultra high res OCT works. And then you have ultrasound imaging. So ultrasound, again, based on different megahertz of imaging. So you have like kilohertz imaging range. Sorry, what am I writing? So you have like kilohertz imaging ranges, and then you have megahertz imaging ranges. Based on that, you have like ultrasound. So here, clinical ultrasound, what we have been looking upon till now, it's like 2 to 10 megahertz. But for therapy, people also go into a lesser low frequency ultrasound, and for high frequency imaging for superficial structures, they also go till like 30 megahertz. However, the resolution based on lower frequencies, it goes till like 400 microns, whereas when it's higher frequencies, it is also proportional to 20 to 40 microns. So that's like the ranges of differentiation that you get. Also depends on the point spread function of the imaging field and of the transducer that you're imaging on. Then you have a high resolution computed tomography, but of course, computed tomography is all about cross sectional imaging. So the resolution there won't be as particular to what we have seen just now, but it would be higher. But 300 micron for an entire organ level imaging is not that much. You'll be able to image vessels, aggregates, and then agglomerates of cells there, bigger tissues, smaller tissues on order. So those things you can image. And then again, MRI. So MRI and CT, more and less, they are always on the similar sides. For MR, again, the magnetic field that you are emitting a tissue for at, or let's say MR also has different gradients of magnetic fields, and then you have different coils. For head, you have a different coil. For your hands, MRI. For your legs, for your entire abdominal, you have different coils. And on those coils, there are like those detectors which will converge the field and source and detector combination, which will like converge and take out the field. So those are like something called as collimators there. Okay. So this is like a one such good image of how to show how resolution and image penetration depends on. So confocal is like a very small region followed by you have OCT, high frequency ultrasound, and standard clinical imaging modalities, which follows like CT, MR, and then X-ray does not go into these regions because getting an sensitivity of an X-ray image is not as sure because there are no so you do not have an exact area where you'll have a focus natural focus where x-rays will converge. So x-rays are like how principle of x-rays work is like we'll see after some time, but those are like beams which are very divergent. So divergent beams do not give you much higher resolution, and the resolution cell there that we are looking at is on much higher scales on order with respect to your other imaging modalities. So in case of x-rays, it's just a confirmation modality, but towards when we go on for this higher expensive modalities as CTMR, there you get an approximation, and then you have ultrasound, which is like point of care imaging, and then you have the smaller imaging modalities. The smaller and smaller you go, the expensive it becomes. And even CTMR are very expensive, whereas X-ray and ultrasound aren't. But X-ray is like an ionizing radiation, and the MR, ultrasound and MR aren't. So that's like a progress how it had happened. This is like one such study case for chronic kidney disease. So, and there was a study population of this, and then they did this all imaging modalities. They got like data from all and did the pixel based analysis, voxel based volumetric analysis there. And radiomics here basically tends for that you have like all scattering features, all um, L, um, mm, Yeah, those are basically scattering features. So you have like all scattering features, all Hounsfield units based on cities. You have X-ray attenuation coefficients based on city. You also have a cross-sectional attenuation, and then you club all of these features all together, and then use like a simple support vector machine or a random forest-based classifier, and you'll be able to see if using the simple, let's say, first order statistical features, are you able to differentiate or not, and can in real time you can help a doctor make a decision intraoperatively during the surgery if he or she wants to, rather than like pausing the surgery there or saying that okay, let's just do it after some time and then first get the test of that particular modality because it was not processed at that time that he wanted to look at. Then pathological diagnosis is of course like a gold standard that we have been using till now, and there are like no such other alternatives next to it. But nowadays, with respect to the solid tissue pathology, people are also doing like a liquid biopsy based methods where they do analyze the blood sample, and that's like very quicker in terms of seconds. So these analysis techniques, how multiple startups have come out and they do work on it, and like the minimum time that I just heard from one of the startups yesterday in a seminar was like 5 to 6 seconds for to analyze one blood sample, and there you go, you have a blood report with you. So now the doctor knows which particular organ now he needs to go to and how with which modality should be best for him to image it with. Okay. So with that, we'll just start with X-ray. We'll conclude on CT, and that will perhaps will give us like a 30-45 minute amount of time to discuss for the previous year's assignment. Okay. So X-ray, as you all know, it looks like this, and now your doctor will give you multiple positions for this particular radiologist to image you at. So in this particular bed you sit at, and there you aren't allowed to take any metallic items if you have with you. So they ask you to remove your watches, chains if you have any, something of hair accessories, or your belt, or if your shoes has something, all of those sort of things. And now then you go there, sit there, you do your hands in some order if you want to image your elbow for some fraction and all. So now for our particular body there are multiple planes of imaging. Some planes which help you differentiate in between left and right are called as sagittal planes. Planes which help you differentiate in between up and down, which are like through and a longitudinal cross section of your body, not cross section, but yeah, a longitudinal bifurcation of your body. Those are like axial planes. And some planes which help you directly like differentiate. So you cannot draw here in 3D, but yeah, it's like the front part of it. So going out of the plane and going inside of the plane. So that's something as a frontal view that you look at. Okay, so doctor gives this radiologist instructions in a way that okay, I need this particular section, I need this view, another view, and then the radiologist asks us to move us in certain uncomfortable manner, and sometimes that we don't even like to, but because the doctor wants to say. Now, for X-ray, you might have seen that they do not require any such distance, and the source is always very as far as possible from the patient. It is not close to us because these radiations are not at all good for us, and they do not even advise if you have like taken an X-ray twice perhaps in a month, they don't advise you to take more than that after, and they'll just say you that okay, keep a gap, and after that only you'll allow to, because these are like ionizing radiation. After some point, if these do interact with our cells, they might even cause us cancer. Not saying it that but yeah, it is that dangerous to our body. And the detector is as close as possible to us. They do hold these films, if you do see, those are like negative films, so that the energy directly falls on them and they may make a portrait of the similarly will process it. So that's how X-ray goes into. And this is this small detector film that you're looking here. Okay. Oh, one graph didn't come here. Let's just open the presentation. Yeah. So here what you see, I won't be able to write in this because it's not allowing me to. But yeah, so on the left you have a anode. So these are like two different, if I can present it here, it will be on full view. Yeah, yes. So on the left you have this anode, and on the right you do see, oi, Can I do a pointer? No. Okay. On the right, you do see a cathode. So how here, how in X-ray it works? So for other modalities is always that you will have multiple electrons going from here and there. How for X-ray you'll heat up the filament to generate electrons there. So at cathode you'll heat the cathode too much, giving it a sufficient kilo electron volt of energy, a potential difference, a potential of energy, sorry, at the cathode, so that it will generate electrons, and those electrons will are nothing but negatively charged, so they'll get attracted towards anode, and the angle in between both of them is so that these are like 45 degree inclined, both of these anode and cathode. And when these electrons strike it, so if that's a heavy metal inside, it can be tungsten ion or something, then this x-rays are the waves which are like emitted divergently below it. So the angle where the in between the incident and reflectance, you do see a 90-degree angle of reflectance there. That's how you do know that those are the x-rays which are being emitted divergently. So that's how it works. Like, and to keep the system cool, you do have oil, then you have a lead casing, so to make it an insulator, you have glass there and a complete window to see X-rays there. So that's how very simple setup of how X-ray work. It's not that complicated. Followed by X-ray, the same thing was taken up by CT, where you had this a big gantry, and then you'll have like multiple sources and detectors. You will have it in like even and odd order configurations, and then multiple sources will like emit your energy, and from how and which particular plane they are being ejected at, the doctor knows that like very particularly there at particular angle only your detectors are placed at. So like at times you do see that they are asking you to bend on, so you do have this sagittal position. At times you do like you're directly laid on, so it's like a frontal position that you're looking at. So that's how this also works. So next time when you go and have a scan, you'll know these things and how it's working actually. Now, whenever these electrons are being interacting with our own body, there are like different effects which are occurring. So when the energy is very lower, it's a photoelectric effect. That just means that it's giving rise to one form and another form, the electrons being jumping from one layers to another. But when it's like interacting with your tissue, it's the Compton process. Much of the energy, whenever your X-ray, not ultrasound, but X-rays are being absorbed into your onto our body, and that's the energy which is being led is like a Compton scattering, or it's like partially absorbed, and that's also Compton. So as you know, like as energy is h nu, or it's also given as hc by lambda, where h here is the Planck's constant. So in this particular energy is like inversely proportional to the wavelength, and this energy would be maximum where your wavelength is minimum. In those cases only you do see this Compton scattering or Compton process being occur. When it's not the case, then that's photoelectric effect where your lambda is greater than the minimum lambda that you have looked at, and hence your energy would be less than the maximum energy. And for pair production, that usually works where you do some PET kind of imaging, that's like positron emission tomography. So there, what doctors do is like they'll emit a radioactive contrast kind of substance into your body. They'll ask us to drink like something based on bromium iodide or those kind of materials which are like which will give them a reflectance when in our body. They do have a half-life after some, so these aren't like that dangerous to our own body, but since it's radioactive, do have some nuclear fission and fusion going on into it, so that is also quite risky. But given brodium some complex of bromium and iodide, so whenever they go into our body, they have like a half-life of 120 and 130 millisecondish. So they do get decomposed after a time through our regular circulatory routes. I don't know. So after that point, doctors won't be able to see it through the route that they were looking at. So that's more of pair production, and it's only needed in some kind of cancer cases where they're looking at chemotherapies and all. So it's not needed for all cases, and doctors also don't even prescribe us to do it as much often as it should be done. Okay. Next, coming on to computed tomography. So that's like a gantry of tomography that you see. And this kind of machines are usually at the bottom layers of your hospitals, are never on the top layers. If you are like, if people here are like part of biomedical program or bachelor's doing, and if you sometime get an opportunity to do an internship at hospital, go and do see this department. So these machines do look fancy and like a very big machines. They are always on the basement floor because you do need much higher electrical insulation there so that you won't affect the other departments and the patients also. So whenever you do need the scans like this, patients are like brought from the upper higher floors to the basement to do the scans. And nowadays governments has also like we do have built our inbuilt India's first own MRI um, from an IIT Bombay based startup that's like Samir. So they are building our own 1.5 to 3 Tesla MRI there. So we are also going ahead into this medical device based sector, but as you all know that most of the devices that we do get, those are like imported, are always from like US, America, US, or mostly from Europe. Our sector of buying these machines are from there, hence the cost of these devices and doing one particular scanner is also higher. So how city works is also on the same thing that you have an X-ray tube. So that's a collimator that I was talking into. So that helps you focus and converge the beams of X-rays that we're going through. And when you look at it at a cross section, like let's say an upper view, it looks like this. So you have this your X-ray tube, and these are like the detectors placed circularly and multiple detectors. So now which part of it detector the X-ray will be passing through, that detector will detect it, and eventually you do an analysis for it. Now, how to do this analysis? You have something as radon transform, and Professor did explained it in a bit more manner that it's nothing but a line integral, and it will help you compute the attenuation coefficients, the attenuation or the mass transfer fraction across a line that the X-ray has been passed through. So both X-ray and CT are like based on X-rays principle, and this principle is also in line integral, which will compute the projection of our attenuation coefficient matrices along a specific axis that you're defining it to. So in this case, this axis here we are taken. So a row in this case, a row here is nothing but here it's not marked up. So a distance from the origin to a point that we are looking at, and theta is the angle in between the source and the line of this projection axis that you'll be looking at. Towards the end, whenever you do radon transform, it usually maps that if you have multiple angles, those angles would be mapped as like a combination of Euler series. Okay, so for more information into it, you can just go and have a look for CT's lecture, and that's like last 10 minutes of the slide are just of the lecture are based on these two things. Then for CT, it's based on filtered back projection, and there are multiple algebraic based reconstruction that have been doing till now, and all have like a similar based of what do you say, resolution of processing. So in this case, how they do is like you have a convolutional kernel, you filter it, so you have the Poinsot function of your X-ray beam that's being passing through, you multiply both of them, let's like convolve basically both of them, you do get a projection, and this projection now in multiple angles, because now your city was like a circle based on circular detectors there. So now you make up an image with respect to this projection from multiple axes. How it works is like basic matrix based processing. So for a particular matrix, you take multiple projections out of them, you essentially sum up them. So that's nothing but advanced form of radon transform that we are essentially looking at. So this integral is nothing but summation of this axis at each and every length, at each and every cross section. Okay, now talking about that, since I mentioned attenuation multiple times here, so I thought let's just also see attenuation how it is through. And for X-ray and CT, both of them like behave differently. Okay, now for when we are talking about X-ray, it's just the sum across all of the tissues, and this diverging beams are just we are like capturing all of them all together. Whereas when it's like a city, it's since it's like a gantry based system, and one at a time it's being done, and it's like a 3D cross section imaging that you're doing there. Now in this case, what you're looking at a volumetric element instead of a 2D pixel element. So this volumetric element is called as a voxel, so it will solve for each of it. Now, image signal in terms of X-ray is dependent on the thickness that it is passing through, as we just saw in radon transform, so you can link it to it. And then for city, it is independent of the thickness. So every time your attenuation won't be dependent on the amount of energy won't be dependent on the thickness that it's passing through it. Because here, what we account for and how we normalize it is with respect to attenuation of water. So that's nothing but the definition of Hounsfield unit that we had previously. So for X-ray, how it works is like X-ray has minimal for air, and then it goes on till bone, so that's higher and thickness followed by sorry. Similarly for the city also. So now you see the same scan of chest in X-ray and CT, but you do see that here in CT you're not able to see bones, whereas X-ray you do see those bones there. Now what happened? How is this different? So that's all because of the volumetric elements and the single pixel based elements that you're looking at. And since it's summing up there, and this is like taking into it all out at a time. Okay. Now here. This is X-ray image. So here you look in the bones. So why do you get such a contrast here? This contrast is because of attenuation. The difference in attenuation in between different tissue layers. That's because of how this photon energy interaction is there in between tissues. Okay. So bone which are like highly attenuating will give you much more higher absorption. Hence those are like a higher pixel intensity weighted, whereas tissues which do absorb some part of the energy of it, sorry, of X-rays, so they are like gray here, and air backed is so much more lesser absorption, so that's like black. So that's how you see, and you'll be able to differentiate. So in some cases, if you have problems there or anomalies there, doctors do know that how this modality work and how it propagates with tissues, how it interacts with tissues. So they do categorize and differentiate it with respect to it. Then you have CT image. So now in CT, you do look at that you are able to see these ribs here, multiple different organs like below it. Now for CT, it's always that where do you want your sources to be focused at. So you do have like three planar, like three images here, three different views of the same frontal view that you're looking at here. Now, here in this case, at first we were looking at the top section, then later we focused on the middle one, and then later on the below one. So, in these cases, we do get different contrast in different settings. That just because of focusing in this one cases, and you do see that how bones look brighter in here. And now you might question that why did the first one, the previous one was looking like this. So, this here, there's this image is after, so that's like an end image, the filtered back projection image, hence you're getting a very clean image, and in below you do see this white dots in here. So if you adjust the scale bar to see, you'll be able to see the bones in those cases if you decrease it, whereas in this case it's like very first preliminary scan. So this is like from my research directly. So this is like raw data that I'm showing you here. So hence how do you look at different planes and angles over here? Okay. So that's all. If you do have any questions, you can unmute yourselves and let me know, or else I'll go on previous year questions and we'll solve them together. So I've given mic access to all of you. You can unmute yourself whenever you want to. No questions? So then for this week's assignment, I do hope that if you all have like went through the lecture slides and you do know all about it because there are no questions. So I'll ask you to give me answers then. So the questions I do have are not exactly on X-ray city and what we just learned now. So that was like an extra information for all of you. But these questions are more from your exam point of view. And since this week, this course is like a 4 week course, but personally, I did felt when I was going through the lecture slides that it was more of an 8 week course, and it had much more in-depth information that it had to be. So if it had to be spanned towards 8 weeks, it was better for like learners like us to follow it through, because in 4 weeks it's a lot of information that you're getting in here. It's also a good course to look at. Okay, so the first question is, in optical microscopy, as the numerical aperture is increased, what happens? So do you all know how numerical aperture changes and what's the formula for numerical aperture? How do you see the depth of field? Has anyone ever used an optical microscope? Anyone? Image should make this. Good. So this numerical aperture is nothing of your in objective slide that you're looking at. Okay. And how this numerical aperture is defined as is n sine theta. And how this increases, your resolution increases. But your depth of focus is proportional to inverse of square of your numerical aperture. So with this information, will you be able to say that what happens if numerical aperture increases, is our depth of focus, what happens to our depth of focus?
Decreases.
Sorry?
Decreases.
Yes, so our depth of focus decreases. So that's option B. Then for this cases, identify the imaging modality that you're looking here at. So we didn't go through them, but yeah, I'll just give you an idea. So T1 images, T1 weighted images in MR, and there are like T2 weighted images in MRI. So these are like slower to make, whereas there are differences of the CSF that occurs into it. So there are like different proton spins interaction there, but just for you to directly identify this based on the images, CSF will appear darker when you have like T1 weighted images, and it will appear brighter when this images with what do you say, T2 weighted images. So there are contrast differences because of an extra half spin in terms of T2, but how it works we'll look at in the lecture in more depth. So in this case, the CSF is nothing but the ventricles that you are trying to look at. So, and then CT, you all know that it's like essentially normalized whenever we always have a look at CT. So, giving this information, what do you think? Which one is which one? So, in CT, the bones will have an highest intensity, which you do see like in A and D. Okay. And then the T2 weighted images with more water content, or let's say as in more CSF, the ventricles which have more water there, those would be brighter. So can you guess now?
A and D is CT,
Mm-hmm.
and B is T1, and C is T2.
Ah, yes. So that's option CT, T1, T2. That's option B.
Excuse me. Can you? Hello.
Yeah, yes.
Can you please explain again, like why is this like B option T1 and C T2 again?
Yeah, so how proton spins appear in T1 and T2, that will go through when we learn about MRI. But one point to understand when it comes to T1 and T2 is that T2 weighted images will appear more brighter because when you have more water content, and the CSF in ventricles, that would be more brighter, whereas T1 weighted images do not. And for that, to account for physics, there you do have an extra half spin of proton in T2 weighted images, hence they look brighter. So here you do see this are brighter, this is brighter, this is brighter. With respect to this, the whole image is being darkened up. So that's how you differentiate in between T1 and T2.
Okay, okay.
Okay. What kind of microscope is used for fluorescence imaging? So here I'll just give you one hint that for this is a fluorescence imaging. It's not something. So how fluorescence imaging works is that you give some energy so that you excite something in your specimen, and it will excite a light at a particular wavelength so that your objective, your aperture will capture it through. So in this case, what do you think? Which kind of microscope do you need? Do you need a transmission or both or a reflector?
I mean, both.
Both transmission and reflector.
Yeah, so when it's fluorescence imaging, you do only need the reflected light microscope.
Reflected light, right?
Sorry?
Reflect,
Yeah,
reflected light microscope
yes.
only.
It's only reflected light microscope because what's interested into you is the excited wavelength that you're getting back into your objective aperture. You're no longer exciting it. You're just looking at that wavelength filter, but microscopes are just essentially used to see into it. So that's a reflected light microscope.
Here are we using laser beam or which what you are going to use as a source of light?
So,
Is it laser?
how microscopes do work is you're not exciting it with anything. You're
No,
just
no. So you need
imaging
a
them,
source, no,
looking.
source of light. For reflection, you need a light, and that light is going to be the laser,
Your bright light, your white light.
white light.
Yeah, yes.
Like, can you give one example where this both transmission and reflected light microscope is used?
So if we do see, they'll be used in confocal microscopy for sure. For like a direct example, let me think. So, okay, so, uh, I, but that becomes more complex. Okay, so there are, so I don't know if you have heard about. So you have like surface-based imaging, morphology-based imaging. That's like SEM, surface electron microscopy. Then you have TEM, transmission electron microscopy, where you do transmit. Then you have something as AFM, atomic force microscopy. So for the first one stands as like scanning electron microscopy or surface electron microscopy, you're just imaging them through. The second one is transmission electron microscopy, you're sending something. Third one is atomic force microscopy, where you're sending an energy, you're trying to change the orientation of the cells and essentially trying to measure the amount of force that you have dissipated there. But that's also more of a surface morphology based technique, and then you're measuring it back. So in that case, it's like both transmitted and reflected microscopy. I don't know if it was that intuitive enough, but perhaps with some examples, you might be able, you can just Google it out and see for more relevant examples that you want to. That's how I was able to just get up now.
Okay, thank you, thank you.
Okay, next. In which of the following materials is the speed of sound lowest? So when it talks about speed of sound, that's essentially sound speed in so ultrasound, that speed there. So is it lowest in air, water, adipose tissue, or liver?
Air,
Sorry?
air.
Air,
Yes. So it won't
in
be able to propagate. So that's just air.
gas is low.
Yes. And then gases do have higher density. The bulk modulus is also higher there, so it won't be able to pass through. Okay. Attenuation of sound is lowest in where? Water, adipose tissue, liver, or muscle?
Water.
Machine. Water,
Yes.
water.
Yes. because in other tissues you'll have multiple layers that will pass through it, might perhaps be absorbed also. Okay. So for the following materials, arrange them in increasing order of attenuation here. So you have liver, you have bone, you have a tissue, and like you have a fat tissue and you have a brain tissue.
Option C.
Yeah, so in this case, if you're looking at option C is like more of a relevant answer here. That's true. But like bone, of course, always would have a higher attenuation. Liver also can be in between, but this placement of how your brain tissue and your adipose tissue is being kept is very ambiguous, so I'm not sure of it, because brain is more of a diffuse and heterogeneous organ with respect to your liver is more of a vascular organ. So in the order, if it was like something as D, C, A, B would have been more accurate, but in this case being like considering both intuitive. Okay, then you have T1 T2 weighted relaxation. So what do you think, which ones like take a longer time and take a smaller time for being formed in MR? So T1 here,
T1 is long.
yes,
T1 is
so
longer and T2 is shorter.
shorter, yes. So T1 here is like a sorry, it's a spin lattice relaxation. So it involves an energy exchange with a lattice, which is like a generally slower, so it takes time to form. And whereas T2 is like a spin relaxation, so with its own phase and coherence, so it's generally faster. Okay. Next, which tissue among the following has highest T2 value? So that's more of a direct question, but okay. So this was like in lecture slides. If you want to go through lecture slides, which lecture it would be? Something of lecture 3 if in MR, and it was like probably first 10 to 20 minutes you'll have this value there. So it's there would be a table for it. So that's for white matter.
What? Yeah.
Okay. Then you have a T2 weighted MR image. So we have denoted white matter regions as W and gray as G, CSF regions as CSF. Then what do you think? Which one? So in a T2 weighted images, okay, that we just looked at now. We just had this answer. So how is CSF with respect to white and gray matter in a T2 weighted image of MR?
Darker
That's brighter,
than.
more water
Oh, sorry.
content.
Yeah, yeah.
Okay. So which of the following modalities are related to nuclear imaging? That's like more of a giveaway answer question.
PET.
Yes.
PET.
With PET, you also have something as SPECT. So if you're free sometime, might also have a look at SPECT. Okay.
Spectre.
Okay. Then what's the frequency of probe, ultrasound probe being used if you want to image a fetus? Would it be a high
3 megahertz.
frequency or lower frequency?
Low. Lower
Yes.
Lower,
frequency.
3
Yes.
megahertz.
Exactly. So low frequencies, you use it for for deeper organ imaging, whereas this imaging is more of clinical ultrasound frequency. And this is not at all used into clinics. That's more of a research-based frequency.
Mm.
Okay. So here they are asking us to identify the views of axes. So these are like MRI scan slices of human leg. What do you think? So looking at B, it's more an obvious, but A and C.
A is spaghetti. Spaghetti.
Hmm.
Sagittal and C is
Sagittal
coronal.
and B is colon.
Exactly. And this is action.
Colon.
Let's see. Okay. So of all the tissues and materials found in our body, which one has the highest linear attenuation in X-ray?
A compact bone.
Yeah. So attenuation in X-ray passing through any material depends on what? So attenuation depends on both factors as mu
decay
and L.
coefficient. Yeah, and length.
Exactly. And the length. Whereas CT doesn't on the length. So it's only dependent on mu. Okay.
Yes.
The darkest region seen in an X-ray image correspond to what?
Air.
Yeah.
Because the attenuation there is very less.
Yeah.
Yes.
What's the radio density of bone? So this is something you might have failed to calculate it. If the attenuation coefficients of bone and water at this. So you know how to calculate the Hounsfield unit of radio densities. So formula goes as for Hounsfield's, it's like XY is 1000 times of the tissue we are interested into minus water by water.
It's A. Option A.
Option A.
Yes, I
Okay.
think so.
Everyone on the same page? Yeah, option A. Okay, which of the following is not a CT construction technique? Like all are. Algebraic sort,
Yeah.
sort, all are. Is this a problem? Like, it says D, but D was also mentioned in the slides. Hmm.
Yeah,
Like
all of them are like,
All are.
yeah,
I
yeah.
also think that all are. Probably this would be a wrong question. Or it would be all are.
Most probably, most probably.
Which among the okay, so this type of questions won't come in your exam. That's like what I said. And
So like,
the top three are like conferences, not even journals. So none of this here.
okay.
no, no.
Okay. So magnetic field of hydrogen is a result of what? A spin of electron or proton.
Both.
Hmm?
Both.
What is a
No,
hydrogen? Is it an electron or a proton?
it's a proton.
Mm-hmm. It's a
Uh-huh.
Both.
positively charged.
Positively charged. Yeah. Proton.
Oh,
So that's a proton. Why?
magnetic field.
It says both.
Yes, hydrogen is having both electron and proton, right?
But it does have only a positive charge in its core.
It's plus. How much
Huh.
plus?
Okay. I guess,
It's
let's
having
go check MRI slides. I do think it's spin of proton, but if it's saying this one,
of
stick to it then.
don't know.
Okay. So of the two MR images, which one's T1 and T2? Now it should be easy for you to recognize.
One is T1,
And the second one?
T2.
Yeah, yes.
It's more
So
defined color.
it's like this one. Okay, so I guess yes, we are done with this week's assignment. You'll be able to solve this pen question. I was confused. This journals question won't even come. This one also we'll have to see because like essentially all are. And if it does say, but yeah, all algebraic techniques fall into it. And the other questions were you were able to solve them. So if you do have any questions, stay back. You can ask me. Or else thanks for joining. It was a nice session.
Okay, thank you.
Thank you.
Can you please again explain this T1 and T2? Why is T2 brighter and why is T1 light? I mean, darker.
So if for simply, if you just need to understand between T1 and T2, so one is like a spin lattice interaction. So if you do have a entire 3D lattice there, and one is a spin-spin interaction. So you are interacting with the same one. So in this case, whenever it's interacting with the entire lattice, our own spin, it does take time to form it. Hence, it was longer also, and it's being normalized into all directions. So it does not have an eventual drop of energy or changes in echogenicity there. Whereas when you're looking for T2, each spin of one proton is interacting with spin of another proton there. So in that case, it is highlighting the differences and the attenuation in between both regions. So hence it in this case, it becomes more brighter and this becomes darker eventually. I hope
Okay.
so.
Okay. Yeah.
Okay, so
Okay. Thank
eh,
you so much. Thank you.
yeah, thank you. If the rest you have any questions, you can let me know. Or else, thanks for joining today. I'll be closing the session then. Thank you.
Thank you so much. Thank you.